This is your presenter Asloob Mudassar, and I am presenting slide number 137 of the course on laser physics. Question is, ion lasers form an important category of laser systems. Discuss two important laser systems of this category, that is Argon ion laser system and Helium Cadmium laser system. The answer is, an ion of an atom has energy levels more expanded in comparison with the energy levels of the same atom. The outermost orbital electron of an ion sees the nuclear charge equal to 2e due to the screening of the nuclear charge by the Z-2 inner electrons. You know that one electron, the atom is ionized, so one electron is moved, and now the outermost electron will see as if there are only two electrons, that the nuclear charge has a charge equal to 2e, because the rest of the charges, that is the Z-2 inner electrons, will screen the nuclear charge. So the outermost orbital electron of the ion sees the nuclear charge equal to 2e due to the screening of the nuclear charge by the Z-2 inner electrons. The lasing photons emitted between two laser levels of an ion will have greater energy in comparison with the photons emitted between the same lasing levels of the neutral atom. So this is very important, that with the neutral atom, that is with the ionized atom, you have an energy emitted between the same two levels with greater energy as compared with the photon energy emitted by the same lasing levels of the neutral atom. If a neutral atom lases in the infrared IR region, its ion may lase in the visible or ultraviolet region depending upon the size of the atom. Ion lasers, like the neutral atom lasers, are categorized as ion gas lasers and metal ion vapor lasers, with examples of argon ion laser and the helium cadmium lasers respectively. Next, we discuss the argon ion, which we may simply call as argon laser, and the helium cadmium laser. Argon laser. So when we talk about argon laser, it means that we are talking about argon singly ionized laser. Energy level diagram of an argon ion laser with the indication of essential laser levels is shown in figure number 1. The neutral argon atom has 18 electrons with the electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6. The form of an argon ion. To form an argon ion, one of the 6 electrons from the 3p orbitals is removed. So this is the last, is the 3p orbitals having 6 electrons. One of the electrons will be removed, and then we are left with the 3p5 electrons for an ionized argon ion. So let's first discuss the energy level diagram of the argon ion laser with 4p and 4s as an upper and lower laser levels. First of all, notice down that the argon atom has a ground state, which is 1s2, 2s2, 2p6, 3s2, 3p6. So when this argon atom is ionized, then of course we get an argon ion which has a ground state over here, that is higher in energy state than the ground state, because this is a singly ionized argon ion, and the electronic configuration of the last 3p orbitals is 3p5. because one electron has been removed from the 3p6 and we are left with the 3p5 as the electronic configuration of the argon ion. So you can see that in the figure we have two levels. One is the 4p level, which acts as an upper laser level for the argon ion lasing system, and the 4s level acts as a lower level for the lasing ion system, for the argon ion system. This 4 level is split into many levels, and similarly this 5s level will be split into many levels, and the lasing action will take place from one of the 4p or one of the levels in the 4p to the one of the levels in the 4s levels. So 4p levels contain many sublevels, 4s contains many sublevels which we have not shown, and we have shown the lasing action from one of the 4p orbitals to one of the s orbitals. Apart from this one, we have shown the metastable levels. These metastable levels you see that are very close to, are not in resident with any of the 4p or the 4s orbitals. And you can see that there are three ways by which the 4p, that is the upper laser level of the argon ion laser, can be populated. One is through A, the path through A, which is the collisional excitation. So the argon ion through collisional excitation is excited to a level, to a 4p level. Similarly, the argon atom can be excited to the levels above the 4p levels. For example, these levels which have been shown in dotted. And once the higher levels, that is the levels above the 4p levels, are excited, then they de-excite through the path B, and then contribute to the population of the 4p level. And we have the metastable levels. The metastable levels are obtained, are excited through collisional excitation. And once we have the metastable state, then of course during the interaction of the ion with the in the presence of the metastable state, the argon ion is excited through the path C. And then of course the population contributes to the population in the level 4p through the path C. And this is through the metastable state, which is the state of an atom which is achieved through the collisional excitation. That is the ground, that is the argon atom in the ground state is encounters an collision, and due to that collision the metastable state gets populated, and this metastable state through a collision with an argon ion the transfer of energy then takes place from the metastable level to the 4p level, that is upper lasing level of the argon ion laser through the path C. So let's read the text to get more information. The ground state electronic configuration of the argon ion then becomes 1s2, 2s2, 2p6, 3s2, 3p5, because one of the electron has been removed, and then we are left only 5 electrons in the 3p orbitals. Many levels exist in the energy level diagram of the argon ion, but only 3 levels have been shown. That is the 4s level, the metastable levels, and the 4p levels. So 3 levels of the argon ion have been shown: 4p level, 4s level, and the metastable level. These 3 levels have been shown. Otherwise, there exist many levels, but these 3 levels are very important for us because they explain the mechanism of the lasing action from the argon ion. When argon ion is excited to 4p level, then excited electron interacts with the remaining 3p4 electrons. So you see that we have the 5 electrons in the 3p orbitals in the ground state of the argon ion, and one of the electrons is excited to the 4p levels, then of course the remaining electrons in this orbital will be 3p5, which are 3p4, which will be the unexcited electrons. So when an argon ion is excited to 4p level, then the excited electron interacts with the remaining 3p4 electrons. the 4p level is split into many sub-levels. So this 4p level, this one will be split into many sub-levels. So only we have shown one level, but in principle there are many sub-levels at the position of the 4p level. And similarly for the 4s levels. The 4p level is split into many sub-levels. The same is true for the excited 4s levels. The lifetime of the 4p to 4s transition, which is the radiative transition, is nearly one order of magnitude larger than the radiative lifetime of the 4s to 3p5 transitions. So you see that if we consider the lifetimes, then the lifetimes of the 4p to 4s radiative transition is one order of magnitude higher than the lifetime of the transitions from the 4s to the ground level of the argon ion. So one order of a magnitude higher. Thus, the lifetime of the 4p to 4s radiative transition is nearly one order of a magnitude larger than the radiative lifetime of the 4s to 3p5 transition. So the lifetime of this transition is very higher. The lifetime of this transition is very high in comparison with the transition of the 4s to 3p5 sublevels, which means that this 4s level will act as the lower laser level in the sense that it has a shorter lifetime, whereas the lifetime from the 4p to 4s is one order of magnitude larger. It means that the population inversion will be achieved automatically for the 4p sublevels, for the 4p levels, and for the 4p sub levels in comparison with the 4s or its corresponding sub levels, because they will decay quickly to the 3p5 levels. So these three, the 4s sub levels and its corresponding the 4p and its corresponding sub levels, will act as a lower lasing level, whereas the 4p and its corresponding sub levels will act as the upper laser levels of the argon ion laser. The 4p level with the high population qualifies as the upper laser level, whereas the 4s level qualifies as the lower laser level. For CW operation, so you see that this is the okay for the continuous wave operation, that if we want to continue continuous laser wave operations, then of course this would satisfy the condition, because the upper laser level has a very higher life in comparison with the lower laser level. So the continuous wave operation can be achieved between these two levels, that is between the 4p levels and the 4s levels. The excitation to the 4p levels. Now we are talking about the excitations. You see that here I have mentioned three paths by which the excitation to the 4p levels can be achieved: path number A, path number B, and path number C. So now we talk about these three paths. The excitation to the 4p levels is achieved by three processes: collisional excitation of the argon ion to the 4p levels directly indicated by the path A. So you see that this argon ion encounters collisional excitation. This argon ion in the ground state encounters collisional excitation and excited to the 4p levels directly through the path A. Collisional excitation of the levels higher in energy than the 4p levels, which radiatively decay to the 4p levels indicated by the path B. Again, you know that the collisional excitation. So collisional excitation of the argon ion will raise the argon ion to the levels above the 4p levels. So the levels above the 4p levels, these levels. And then these levels will decay through the path B, which will be the radiative decay, and then the population will decay to the 4p levels. So these are the two paths that we have explained. Now we are going to talk about the third one. Collisional excitation of metastable levels, which through the collision of the argon ion excite its 4p levels indicated by the path C. So once the metastable states are excited, then the argon ions in these metastable states will encounter with the argon ions in the ground states, and the energy of transfer will take place through the path C. So the metastable states will give up their energy, and the 4 up and the 4p level will be excited. You know that the 4p or the 4s levels, none of them is coinciding with the metastable state levels in energy, because none of them is resonant with the metastable states. Two collisions are involved in each of the above mentioned excitations to the 4p levels. That is, in path A and in path B, two collision processes were involved. But through the metastable states, which involves three collisional excitations to the 4p levels. So two collisional excitations are involved in path A and in path B, and three collisional excitations are involved in path C. For example, in path A, two collisions are involved. One collision is that you have the argon atom, you ionize the argon atom, then you get argon ion. So this is one collision, that is from the ground state of the argon atom to the ground state of the argon ion. It involves one collision. So one collision from the argon atom to the argon ion. This is one collision. The second collision is that you raise the argon ion through the collisional process to the 4p level through the path A. So this is the second collision. So it means that through path A, we have the two collisions. One collision from the ground argon atom to the argon ion, and the second from the argon ion to the 4p level. So two collisional processes are involved to reach the 4p levels. Similarly, we involve the two collisional process to the path B, that is the argon atom or the argon ions are raised to the levels above the 4p levels. For example, these are the levels. Through one collision is that you raise the ground state, that is the ground state of the argon atom to the argon ion state. This is one collision. And the second collision is that the argon ion are raised to these levels, above the levels, upper the levels above the 4p levels. So this involves second collision. So two collisions are involved, and the path B is the radiative decay process. So no collision is involved in this one. So ultimately, in reaching to the 4p levels through the path B, only two collisions were involved. Now in the metastable states, three collisions are involved. One collision is that you have, which is common in all the three processes, is that you ionize the argon atom through the collisional process, and you achieve argon ion. This is one collision. The second collision is that the argon ions are through collisional process are raised to the metastable levels. This is the second collision, and then metastable states are raised to the 4p levels through the process C. This is the third collision. So through the path C, to reach the 4p levels, there are involved three collisional processes. So for the path A and path B, in each of these two paths, two collisional processes are involved, whereas in the path C, three collisional processes were involved, and one collisional process is common to all the three processes, and that is the argon ion. The argon atom is converted to argon ion. This is through one collisional process, and this collisional process is common to all the three processes. First collision of argon atom with the electrons results in the formation of argon ion. The second collision of argon ion with the electrons either follow path A, path B, or path C. That is, the argon ion can be raised through path B or through path A or through path B or through path C. This will involve second collision. The path A and B lead to the excitation of the 4p levels, whereas the excitation to 4p level through C involve another collision. For paths A and B, the rate of upper state excitation, which can be denoted by dN2 over dt through the pumping process. P is at the subscript stands for the pumping process, and dN2 is actually the population in the level in the 4p levels, which we are denoting as N2. So dN2 over dt as the population through the pumping process can be written as shown in equation number 1, that is dN2 over dt, that is the population of the 4p level through the pumping process is directly proportional to two quantities. One is the number Ne, number of electrons present in the number of electrons, and the second is the number of ions, that is argon ions, number of argon ions, and Ne is the number of electrons present in the system. So since in the plasma the number of ions and the number of electrons are roughly equal, so we can regard them as Ne square. In the plasma, the electron and the ion densities are roughly equal. That is why we have taken Ni to be equal to Ne. Following the equation, that is the current density J is given by electron times the drift velocity of the electrons times the number of electrons. So J is equal to E times V drift times Ne. And you know that from here it is clear that Ne is directly proportional to the J, that is the number of electrons present in the system is directly proportional to the current density. The greater the current density, the greater would be the number of electrons in the leasing system. So this equation number 2 is valid under the condition that V drift is independent of the discharge current. So here in writing equation number 2, we are assuming that V drift is not influenced by the current density, which requires that the discharge electric field to be independent of the discharge current. So since V drift, we are assuming here that V drift is independent of the current density J. So on the same basis, we can say that the discharge electric field will be independent of the discharge current J. And under that condition, following the previous equation, that is from equation number 1, that is from equation number here, equation number 1, we can write this equation in the form as given in equation number 3, that is dN2 over dt, that is the rate of transition to the 4p level through the pumping process P is directly proportional to J square. That is the square of the current density. So from equation number 3, it follows that the population in the upper laser level would increase with the square of the current density. So the greater would be the current density, the greater would be the population in the 4p levels, and the greater would be the population inversion. As the 4s and 4p levels consist of many sublevels, the transition, that is 4p to 4s, consists of many lasing wavelengths, out of which the most intense are the green, with lambda is equal to 514.5 nanometer, and the second one is blue with lambda is equal to 488 nanometer. These are the more intense beams, that is their probability of emission from the under this transition, that is 4p to 4s transition, is very higher. So green wavelengths and the blue wavelengths are the most intense wavelengths which are emitted under the transition from 4p to 4s. The Doppler line width, which we denote as delta nu naught star of the green transition, has been measured for a typical system and is reported as to be nearly equal to 3.5 gigahertz. The schematic diagram of a high power water cooled argon ion laser is shown in figure number 2. So next we are going to show you the schematic diagram of a high power water cooled argon ion laser system. This is what you can see. Let me read the caption first. Schematic diagram of a high power water cooled organ ion laser system with built-in wavelength selection mechanism. So you can see that we have these are the anodes in black, and these are the cathodes, and we have powered them through the electric power supply connecting the anode terminals and the cathode terminals. Then you have the plane mirror on this side and a prism for wavelength tuning. This is the prism just in front of, just at the back of the plane mirror. So this will provide you, the rotation of this prism will provide you a tuning mechanism, and you can tune your desired wavelengths. For example, you can tune either you want the green wavelengths to be emitted or the blue wavelengths to be emitted, or the other wavelengths which we have not mentioned, because only the green and the blue were the intense one. So if you want to obtain any of these wavelengths emitted under the transition from the 4p to the 4s level, you can rotate this prism and can select the desired wavelengths. And you can see that this is the output mirror, which is the fixed mirror, and this is the aperture, and this is the side from which the lasing operation can be obtained. Okay, now you can see, let's now talk about the inner of this one. So I have talked about the location of the anode and the location of the cathode. And this is a laser beam, and a discharge current will flow over here. You can see along the beam axis direction. In the center of this structure, you have the laser beam, and similarly the discharge current is present over here. And of course, the plasma is also formed in this region. The organ plasma is also located over here. Then you have this gas reservoir and the inlet valve of the gas reservoir. So you enter the gas over here in this region through this inlet valve. And the other part is that you have a Brewster window on both sides of this structure. This is the Brewster window. This is also the Brewster window over here on both sides. You can convert your laser beams to the linearly polarized beam. So that's why the Brewster windows are there. And you have the water channel over here. This water channel will help to cool down the lasing system, because the water will continue to flow in this region. Then these are the tungsten discs. So these discs are very important. You can see that these all are the tungsten discs. Their structure, their purposes will be explained in the text. And this is the high field magnetic field. High field magnetic field is over here. I shall also be talking about the purpose of high magnetic field and the gas return paths. So these gaps in the tungsten disc provide a means for the gas return path. And this is the ceramic tube. This too, you know that the bracket is about this one. This is the ceramic tube through which the water channel is located, and the high magnetic field is also applied across it. So this was the schematic diagram of the water-cooled organ ion laser system with built-in wavelength mechanism scheme. This is the built-in wavelength mechanism scheme based on prism. So now we are going to explain the structure of this one. Ceramic tube contains an arrangement of tungsten discs with their central holes providing an arrangement for capillary bore. You can see that these are the tungsten discs. These are the tungsten disc, and there is a hole in the tungsten disc over here which provide a mechanism for the central bore, in which the organ plasma or the laser beam or the discharge current over here in the center will be present. So a hole has been drilled in the tungsten discs to have a separation, to have a space for the organ plasma, for the laser beam, and for the discharge current to be present over here. The capillary bore contains discharge current, argon plasma, and laser beam. Anode and cathode are contained at the opposite ends of the ceramic tube in the form of rings. So these anode and cathodes, these are in the form of rings. You can see this is in the form of rings that we cannot draw on a two-dimensional geometry, and the anodes are also in the form of ring and located, you see that on the ends of this structure. Anode and cathode are contained at the opposite ends of the ceramic tube in the form of rings. Brewster windows are also fitted at the two ends of the ceramic tube for polarized beam. One end of the cavity contains a plane mirror, whereas the other end of the cavity contains a rotatable prism and a plane mirror, which I have explained earlier. So this is a fixed mirror over here, and this is the mechanism for the selection of the wavelengths. That is a fixed plane mirror and a plane mirror and a rotating plasma and a rotating prism structure. Both will be rotated together. That is the plane mirror and the plasma, both will be rotated together so that the mirror remains at an angle 90° to the beam which is received from the prism. So that's why both will be rotated simultaneously for the selection of the desired wavelength. The prism is used to select a particular wavelength for lasing and thus acts as a tuning element. The inlet valve on the gas reservoir is used to maintain the required argon pressure within the tube. You see that here, this is the gas reservoir, this is the argon gas reservoir, and the inlet provides you a means to maintain a pressure, a constant pressure within this ceramic tube. The capillary bore has a diameter close to 2 mm for the TEM00 mode to oscillate. The small bore diameter limits the amount of discharge current and thus heating effects are reduced. So let me show you capillary bore. This is the capillary bore in the center. It has a diameter of 2 mm. This limits the output power as well as this will limit the production of heat within the structure. Due to high density of discharge current, some argon ions may head towards the cathode, where they are neutralized by the electrons from the cathode surface. You see that this we do not want that the argon ions should reach the cathode and are neutralized, because this provides us a source for to achieve a population inversion. So we want have their specific value, their number, a specific number, so that we can attain a steady state operation. But you see, and we do not want these argon ions to be neutralized, and we don't want them to reach the cathode surface. Neutral argon atoms pile up in the vicinity of the cathode. This may result in the fall of argon pressure in the discharge capillary. To overcome this problem, some off-center holes are made in the tungsten disc to provide the return path for the build-up of argon atoms to contribute back at the capillary tube. So you can see these holes, these separations in the tungsten gap in the tungsten discs, and these provides a mechanism for the argon atoms to reach to the capillary tubes again and contribute in the process of lasing process. That is, organ atoms are converted back to organ ions in the region of this plasma. So we want that the organ ions which have compiled at the cathode should reach through these gaps to the capillary tube, to the capillary bore. Okay, let me read this again. Neutral organ atoms pile up in the vicinity of cathode. This may result in the fall of organ pressure in the discharge capillary. To overcome this problem, some off-center holes are made in the tungsten discs to provide the return path for the piled up organ atoms to contribute back at the capillary tube. The off-center holes in the disc are arranged in a zigzag path to stop the flow of discharge current towards the cathode. The large amount of heat produced in the capillary discharge is reduced by the water channel in contact with the tungsten discs. The electron produced in the discharge capillary may diffuse towards the capillary walls, which result in the decrease of free electrons at the capillary tube axis. So let me read again. The electrons produced in the discharge capillary may diffuse towards the capillary valves, which results in a decrease of free electrons at the capillary tube axis. To remove this defect, a static high magnetic field is applied. A static high magnetic field is applied in the discharge region parallel to the tube axis. Using a long solenoid, the magnetic field makes the electrons to rotate about the capillary tube axis, confining them along the tube axis and reducing the impact of the electrons with the walls of the tube. That is, with the walls of the capillary tube. So the electrons which will interact with the walls of the capillary tube while they exist in this capillary bore, when they hit the walls of the tube, they may lose their energies. So we want them to remain within the capillary tube without colliding with the walls of the capillary tube. For that reason we apply a high magnetic field, and this high magnetic field keeps the electrons within the capillary tube. The electrons may be spiraling around the lines of the magnetic field, but they will remain within the capillary tube without colliding the walls of the capillary tube. So this is why we apply the strong magnetic field. So the magnetic field makes the electrons to rotate about the capillary tube axis. That is the spiral, that the electrons spiral around the axis of the capillary tube or the center of the capillary tube, confining them along the tube axis and reducing the impact of electrons with the walls of the tube. The mirrors are mounted outside the ceramic tube to avoid any damage to the mirror coatings. And here you can see that the mirrors are outside the cavity structure. This is the cavity structure. And this, you can see, this is the output mirror outside the cavity structure. This is the prism, and the plane mirror are also outside the cavity structure, so that their coatings are not damaged. So mirrors are mounted outside the ceramic tube to avoid any damage to the mirror coatings. For low power organ laser having a power less than 1 watt, the laser tube does not contain water channels and magnets. Such low power organ lasers are air cooled. If an organ laser is operating above the threshold, that is, it is a more intense that is the purpose is more intense beam, its output increases with the increase in current density, and the upper laser level is not saturated in population. because if the population is above the threshold and we are providing more energy, more current density, then of course that will be responsible for the upper laser levels not to be saturated, because the more decay of the upper laser level to the lower laser level will take place and will result in the form of a more intense output laser beam. Quantum efficiency of the Argon laser system is lower than 10%, and the overall laser efficiency is much lower, that is lower than 10 to the power minus 3, because of the levels above the 4p levels are not well coupled to the 4p levels. That is all the levels above the 4p levels. For example, these levels which I have shown in the dotted over here, that is these levels above the 4p levels, they are not well coupled to the 4p levels. So all will not make transitions to the 4p levels. Some will make the transition levels to the other available levels. So since these are not coupled very strongly to the 4p levels, so this will reduce the efficiency of the lasing system. And this is the so we have a very small efficiency of this laser system, because the levels above the 4p levels are not well coupled to the 4p levels. Now argon ion lasers have applications in laser printing, in pumping other laser systems including solid state and dye lasers, in the treatment of diabetic retinopathy, and in the study of light matter interactions, etc. Some applications require the argon ion laser to be used in mode locked operations. So these are the possible applications that I have discussed. Now the next we are going to discuss the helium cadmium laser. Laser transitions occur in cadmium ion. Again, you see that we are talking about the cadmium ion. So the laser transitions occur in cadmium ion. Helium, He, is useful in pumping process. Helium is excited to two 3s and the two 1s states through electron collisions, as in case of helium in the helium neon laser. So the helium in the helium neon laser works in the same way as helium in case of cadmium laser will work. That is the role of the helium in the helium cadmium laser will be the same as the role of helium in the helium neon laser. That is, the helium in the cadmium will also be raised, will be also excited to the two metastable states, two 3s and two 1s states. For the detail of this helium structure, you can have a look at the previous slide, which explains the helium neon laser system. Energy is transferred to from the excited helium to the upper laser levels in the cadmium ion through the panning ionization process, where the cadmium ion levels are not resonant with the excited helium levels. So you see that since our cadmium levels are not in resonant with the metastable helium levels, even then the ionization process can excite the cadmium ions. And this process of excitation is through the panning ionization process, which will be explained through an equation in the next slide. Cadmium atom has 48 electrons with the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, and 5s2. So if you count them, these becomes 48 electrons. So cadmium ion has 48 electrons with the electronic configuration given. Through collision with excited helium atoms, the cadmium atoms are ionized, where one electron from the 5s orbital is ejected. So one of the electrons from this 5s orbitals will be ejected, and only one electron will stay in this one, forming a cadmium ion. So the cadmium ion after ejection, so the cadmium ion will have the following electronic configuration. You can compare the configuration of the cadmium atom with the cadmium ion. You will notice that one of the 5s electron has been removed. Ground term of the cadmium ion arise due to the single electron in the 5s orbital, which has the quantum number. Principal quantum number is n is equal to 5. Orbital quantum number is 0 because s means L is equal to 0. Because you see that this S means that the orbital quantum number L is equal to 0, and since there is only one electron, so we have the spin quantum number equal to half. And the total angular momentum of the atom, which is capital J, is obtained through the LS coupling. So we have capital J is equal to the mod of L plus minus S, and substituting the value of L, capital L, and capital S, which is 0 plus minus half, you will get 1/2. And the multiplicity is given by m is equal to 2s plus 1. So substituting the value of s, which is equal to s is equal to 1/2, you will get 2. So multiplicity is 2, so it means that the doublet. But you know that when L is 0, then this doublet will not be doublet, but it will be a singlet. This is only a special case that the multiplicity is not followed. Multiplicity says that this should be a doublet case, that is the two possibilities of the orientation of the spin and two values of the angular momentum atom and total angular momentum of the atom. We should have two values according to the multiplicity, but since for L is equal to 0 case, this is violated and we have only a single term. So not doublet, but single term will be present. So the ground state has a single term represented by 5, 2s half. This half is the principal quantum number. This 2 as a pre-superscript 2 is actually the multiplicity. This symbol S, capital S, is due to L is equal to 0. Because L is equal to 0 has a term which is capital S. This capital S is the spectroscopic term corresponding to capital L is equal to 0. Because capital L is equal to 0, it means that the symbol will be used is capital S, and this half is the value of the total angular momentum quantum number, total quantum number of the atom, which is half. J is equal to half. So this is the ground state term of the cadmium ion. So cadmium ion has only one electron in the 5s orbital with energy, with the ground term, with the energy term represented by 5 to s half. Water with laser point of view, two higher energy states are important, which corresponds to shifting of 5s electrons to 5p orbitals or to 5d orbitals. So you see that here we are talking about that with the laser point of view, two higher energy states are important, which corresponds to the shifting of 5s electrons to 5p orbitals or to 5d orbitals. So let me show you the diagram so that we can have an idea. So this is the indication of the laser transitions in a helium cadmium laser system. On the left hand side, you can see that the helium atom, the energy terms corresponding to the helium atom are shown. This is the ground state of the helium atom, 1s1. For this one, you can consult the previous slide in order to see that how these were achieved. And these are the two excited metastable levels of the helium atom. 1s and 3s. These were obtained through collisional excitation. And for the analysis of these energy terms, you can consult the structure of the helium as we discussed in the previous slide. That is in slide number 136. Now this is the electronic configuration of the cadmium atom, and only the last three have been shown: 4p6, 4d10, and 5s2. And when one of the 5s2 electron is removed, then the electronic configuration of the cadmium ion becomes 4p6, 4d10, and 5s. So you see that only one electron is present in the 5s orbital, and you see that its energy term is 2s half. I have not written the principal quantum number over here, just only the term has been written, which is 2s half. And this is what I have just explained through the text, that how we can achieve this 2s half as the energy term. You can see that there are other energy terms are also present. So through the panning ionization, the D levels, the two D levels are present. The two D levels gets their population gets ionized. Sorry, not gets excited through the collision with the helium atom. So when the cadmium ion collides with the helium atoms having these two metal stable states, then of course the energy from these metal stable states through the collisional process will be transferred to these D levels, which we are shortly going to explain while discussing the cadmium ion structure. So these are the two D levels which are excited, and we have also the two P levels. These two D levels form the upper laser level, and these two P levels will form the lower laser level of the cadmium ion laser system, emitting respectively 416 nanometer of wavelengths from 2D5 half to 2P3 half, and then from 2D3 half to 2P1 half the wavelength 325 nanometer is obtained. We are going to explain how we can talk about these D levels and the P energy terms. So you see that I am now talking about here that with the laser point of view, two higher energy states are important, which corresponds to the shifting of a 5s electron to 5p orbital or to 5d orbital. You see that we have already this 5s electron. So this 5 electron is excited where either to 5p. I have not shown 5p over here. It's located somewhere above these D levels, or maybe in coinciding with the D levels. So this 5p electron is raised to the 5p orbitals or to the 5d orbitals, even lying higher to that one. So these 5 electrons will be raised to either 4p or to the 4d levels. So with the laser point of view, two higher energy terms, higher energy states are important with the corresponding shifting of 5s electrons from the argon ion to either 5p orbitals or to the 5d orbitals. Now we have to talk about this 5p orbitals when the electron is raised to 5p orbitals or the s electron is raised to 5d orbitals. Let's talk about these two orbitals. Let us consider the 5p state in the cadmium ion. Quantum numbers, you see that only one electron is present in the 5p orbitals. So quantum numbers relevant to this state are n is equal to capital 5, principal quantum number is 5. Capital L, which corresponds to the value of a p, is capital L is equal to 1. And capital S, since we have only one electron, so we have capital S is equal to half. And the total value of quantum number J is similar as in the previous case, that is capital J is equal to the mod of L plus minus half, but not similar because here we have capital value of L is equal to 1 and the value of principal quantum number S is half. Sorry, the spin quantum number is half. So we have 1 plus minus half and we obtain the two values 3 half and 1 half. So two values of total quantum number of the atom are possible in this case. Now the term symbols correspond to capital L is equal to 1 is P. So you see that since we have capital L is equal to 1 in this case, and the term symbol corresponding to capital L is equal to capital P, the multiplicity of the system is again 2s plus 1. So putting the value of s is equal to half, you get a multiplicity is equal to 2. So here you have multiplicity 2 means this is the case of doublet. That is, you will obtain two energy terms or the two values of the quantum number J of the atom. Thus the electron terms, thus the energy terms corresponding to the 5p states are 5 and 2p, 3 half and 1 half. This 5 is the principal quantum number. These two as a P superscript is actually the multiplicity, which is 2, indicating that it is a case of a doublet. That is, two energy terms are present, one corresponding to 3/2 and the other corresponding to 1/2. These are the values of the capital J, that is the angular momentum of the atom, and this capital P corresponds to the value of L is equal to 1. So when L is equal to 1, the term that we used is represented by capital P. Now, the second option is that we have raised the electron from the 5s orbital of the argon ion to the 5d state. So now we consider the 5d state. Again, there is only one electron in the 5d state. Quantum numbers relevant to this state are n is equal to 5. Principal quantum number is 5. Orbital angular momentum, orbital quantum number capital L is equal to 2. Spin quantum number is equal to half because only one electron is present. This gives you J is equal to plus minus 1 mod. Substituting the value of L is equal to 2 and S is equal to half, you get two values of 5/2 and 3/2. And the term symbols corresponding to capital L is equal to 2. You see that we are using capital L is equal to 2 over here, which means that the term corresponding to capital L is equal to 2 is represented by capital D. The multiplicity M is equal to 2S plus 1. Using the value of S is equal to half, you will get the multiplicity is 2. It means that this is a case of doublet. That is, the two values of quantum number J of the atom is available. That is two terms. You see that two values of J are there. Thus, the energy terms corresponding to the 5d states are two terms. 5 principal quantum number, pre superscript 2 is due to multiplicity, capital D is due to L is equal to 2, because L is equal to 2 give you a term symbol which is capital D, and these are the two values of J, 5/2 and 3/2. So these are the two energy terms. Relevant energy terms of the helium atom and the cadmium atom have been shown. Now you see that these D terms corresponding to the 5D states. Now it is very clear that these two terms of D corresponding to the 5D states and the 4P terms corresponding to the two P terms. Here you can see that these P terms corresponding when the electron is raised to 4P states, and this D terms corresponding when the electron is raised to this 5 electron is raised to 5D state. So corresponding to these 5D states, we have these two energy terms, and corresponding to the 4P state, when the electron, if the electron is raised, if the 5s electron is raised to 4P state, then we have these two energy terms. So this will form, the probability of that is the population inversion is achieved in these states, because due to collision with the metastable states of the helium atom, the energy through the panning ionization is transferred to these D levels. So the population of the D levels is higher, much higher in comparison with the population of the P levels. P states. So these are the D energy states corresponding to the 5D symbol, and these are the two energy terms corresponding to the 5P level. And we have obtained, you see that this is what we have explained, these energy terms. The excitation process of the upper state of the laser through the panning ionization can be explained in the following equation. You have the excited helium. Helium is in the form of excitation. That is why a star indicates that a helium is excited to their metastable states. And we have the cadmium neutral atom. This neutral cadmium atom collide with the helium atom in its excited state, and the energy is transferred in such a way that the helium gets de-excited to its ground state, where the cadmium atom is not only ionized. You see that the cadmium ion is ionized, and also an electron is also emitted. The excited helium atom. Now you see that we are talking about the excited helium atom, that is the helium star, in the two 1s and in the two 3s states collide with the neutral cadmium atom, and the cadmium atom gets ionized. The cadmium ion may either be left in its ground state, or may be left in one of its excited states, that is in the 4p state having two energy terms, or in the 5d states having two energy terms. So three possibilities are there for the cadmium atom when it's collide with the excited helium atom. Either the cadmium atom gets ionized, the cadmium ion may be left either in its ground state or left in one of the excited states corresponding to 4p levels having two energy terms, or corresponding to the 5p level having two energy terms, and corresponding to the 5d level having two energy terms. So let me explain through the figure. So if there is a collision of the cadmium atom with the helium atom in its excited state, then there are three possibilities. Either the cadmium atom, this cadmium atom, after collision with the helium atom, gets excited to over this state. That is, it is ionized. That is, the cadmium atom is ionized, occupying this 5s orbital. The second possibility is that the cadmium atom, after ionization, is transferred to the 4p level, having two energy terms. Or the cadmium atom, after colliding with the helium atom, is ionized and is raised to the 5d orbitals, having two energy terms. So three possibilities, either to this state or to 4p, either to 5s state, or either to 5p states, or either to 5d states. These are the three possibilities after the collision. And you know that these two are, for example, especially this one is more favorable for us, because we want these 5d levels, or these two terms corresponding to the 5d levels to be occupied, to be excited, because we want these 5d levels or these two energy terms to be acting as the upper laser level, and these 4p level to be acting as the lower laser level. The rate of excitation to D states is nearly 3 times greater than the excitation to P states. So this is very favorable, that the excitation to 5D levels, that is these two energy terms, is 3 times greater than the excitation of this lower laser level, which corresponds to 5P levels. So this is having a 3 times higher probability to be occupied. That's why the population inversion is achieved. Helium atom in the excited state should possess an amount of energy greater than the sum of energies required in. So you see that this helium should transfer energy to the cadmium in such a way that it should be equal to the sum of three energies. What are those energies? Number one, in ionizing cadmium atom. So the energy that is used in ionizing a cadmium atom, the energy required in the excitation of the cadmium ion, the energy acquired by the ionized electron as kinetic energy. So the helium atom should transfer energy in such a way that it should be at least equal to the energy of these three energy utilized in three processes. That is, energy utilized in the ionization of the cadmium atom, the energy utilized by the cadmium ion to raise it to the appropriate levels, that is the 4p levels, or the 5p, or the 5p levels, or the 5d levels, and the energy acquired by the ionized electron as the kinetic energy. You see that this is the electron that is emitted through the process also, so it should also gain some kinetic energy. So the helium is de-excited, this cadmium ion is ionized, as well as it could be raised, as well as it could be in the three possible states, that is, as well it could be in the 5s state, it could be in the 4p state, it could be in the 5s state, 5p state, or the 5d state, and the probability for the 5d state is the highest. And of course, this kinetic energy should also which is emitted should also take some energy from the excited helium as its kinetic energy. So let me read again. Helium atom in the excited state should possess an amount of energy greater than the sum of energies required in ionizing a cadmium atom, energy required in the excitation of cadmium ion, energy acquired by the ionized electron as kinetic energy. These states possess much longer lifetime of the order of 0.1 microsecond in comparison with the p states, which is having a lifetime of the order of 1 nanosecond. So D and P levels qualify as the upper and the lower laser level respectively for CW, that is for continuous wave laser operation. The optical selection rule is delta J is equal to 0 plus minus 1. So this rule must be obeyed on the value of capital J. So allowing us that 2D 3 half to 2D 1 half transition is allowed, which gives you a wavelength of 325 nanometer lying in the UV region. And the other transition, which is 2D from 2D 5 half to 2P 3 half transition, gives you lambda is equal to 416 nanometer, giving blue light. The cadmium ion then decays to its ground state radiatively, because the lifetime of the p states is very low, so of the order of nanoseconds. So the lower p levels will decay to the ground cadmium states very quickly. So the population, so the lasing process can be achieved between the d states and the p states, which we have indicated through these two transitions. Schematic diagram of a typical helium-cadmium laser cavity is shown in figure number 4. Helium gas and the cadmium vapors are fed to the cavity through a small opening located close to the anode terminal. So let me show you the figure of the helium-cadmium laser cavity, which is over here. The caption of the figure is schematic diagram of a helium-cadmium laser indicating main components of the laser cavity. So let's see the main component of the laser cavity. You see that the helium cylinder and the cadmium reservoir are connected through these common, which are heated and then of course are fed through a narrow tube to the laser cavity. This is the capillary tube. Over there you can see capillary tube where the lasing action takes place. This is the overall glass tube. This is the cylindrical cathode. Cathode is in the form of cylinder. To evacuate pump, to maintain the pressure of the gases, you connect a pump for evacuation. This is 100% reflector over here and a partial reflector over here, so you can get the output beam from this end. This is the Brewster window, and there is also a Brewster window over here which has not been marked. So two Brewster windows on either side to obtain linearly polarized beam. So you can see this is the cathode terminal and this is the anode terminal. This is a bore sport spider to sport the capillary tube. And you see that I have also explained all these one. And now let's read the text to have more insight into the description of this cavity. So schematic diagram of a typical helium-cadmium laser cavity is shown in figure number 4. Helium gas and the cadmium vapors are fed to the cavity through a small opening located close to the anode terminal, which I have shown you over here. So you can see that these two helium gas and the cadmium gas are fed through the opening very close to the anode terminal. The cadmium reservoir is maintained at a temperature of 250 degrees Celsius. The current in the discharge is maintained in such a way that the vapors within the tube do not condense on the walls of the tube, being at high temperature due to discharge. So due to the discharge current present in the tube, the vapors of these gases will not condense. will not condense in this tube, will not condense at the wall of the tube because the wall is heated due to the presence of the discharge current. So the vapors will not condense, but the vapors may condense somewhere. Let's talk about that. The current in the discharge is maintained in such a way that vapors within the tube do not condense on the walls of the tube being at high temperature due to the discharge. Cadmium atoms, however, can condense on cylindrical cathode. So the cylindrical cathode is a process because this is a relatively much cooler, and the vapors can condense over here being at low pressure because the cylindrical cathode cylinder is at a low pressure due to the absence of the discharge current in that region. So the discharge current is absent over here. The discharge current is absent in this region of the cathode cylindrical region, and the vapors and the gas vapors can condense over here in this region. Cadmium ion can migrate towards the cathode. So the cadmium ion can migrate towards the cathode, which we do not want them to migrate. But of course, in the natural process, they do, and are converted to cadmium atoms because of their recombination with the electrons at the cathode surface. Due to condensation of cadmium atoms at the cathode, a continuous supply of the cadmium vapors is injected into the laser tube for long-term CW operation, because the vapors which condense on the cadmium on the cathode tube, on the cathode cylinder, are actually act as a loss of the cadmium atoms. So we need to inject more cadmium atoms inside the cavity, and at the same time we can maintain a pressure through the vacuum pump. So due to the condensation of the cadmium atoms at the cathode, a continuous supply of the cadmium vapors is injected into the laser tube for long-term CW operation. The tube is evacuated to keep the pressure constant within the tube. The laser cavity has isolated optics, for example, Brewster window, mirrors, etc., to avoid any damage to these components. Typical helium cadmium laser can give output in the range of 50 to 150 milliwatt. Typical applications include holography, fluorescence, study of biological specimens, and laser printing, etc. So you see that I have explained here two lasers in this lecture. One laser was Argon ion laser system. The other was helium cadmium laser system. These two have been explained in greater detail. So as far as the helium is concerned, you can see the excitation of the helium and their corresponding energy terms by having a look at the slide number 136. That is a previous slide. So this is the end of slide number 137.